Welcome to our third lesson of our chapter 7-8 Logarithms and Exponential Functions chapter. Today we're going to be using the information from lesson 1 and 2. So that was our log laws, logarithms, and exponential equations to solve word problems. So there are two types of exponential equations you will see: growth and decay. So often you will encounter these types of problems in economics or in science. Those of you who are planning on going into maybe biology or health sciences or kinesiology will often experience these types of equations when you're talking about bacteria or some sort of chemical compound. So we are talking about things growing exponentially or decaying exponentially. So when you've been maybe watching the news about COVID-19, they're often talking about exponential growth. And that's what we're learning about in this chapter, essentially. So exponential growth is what we're going to start with. Example of an exponential growth equation is here. P equals 2.76 times 1.022 to the power of n. So notice how the 1.022 is in brackets. That means the exponent n is only applied to the 1.022 and not the 2.76. Okay. So this is telling us this is the population in BC since 1981. And our first step is here, we want to define the variables. What is P and what is N? If you think about this logically, this is representing the population in BC since 1981. So P probably represents population. And then the question is, well, what do you think N represents? N probably represents the number of years since 1981. So sometimes you'll see a T here instead of an N, but this is usually a measure of time, either years, months, days, depending on the question. The next part is we want to try and explain what's happening here. What do these numbers mean? Okay. So the 2.76 would be our starting population. And it doesn't make sense here that 2.76, there's 2.76 people in 1981. So this is probably in thousands, hundreds of thousands, or millions. It's probably in some other unit, which is often used if you have really big numbers. So the 2.76 would be the population in 1981. And again, we're not thinking that this is actually 2.76 people. That would make no sense. This is probably in tens of thousands or hundreds of thousands or in millions. And then the other number we have is 1.022. And this is representing our growth. The population is growing because this is a number bigger than 1. Okay, so this is representing growth. And so our growth rate is actually this 0.022 here. If I change this into a percent, I would have 2.2%. So this actually tells us our growth rate. And in this case would be 2.2% because of this 0.022 here. So if it said 0.05, that would be 5%. If it said 0.12, that would be 12%. So it tells us how much we're growing by. The 1 represents starting with 100% of what you started with. So the 1 means we have that full 2.76 or 2,760,000 or whatever number that represented. So the 1 tells us we're starting with 100% of what we had, and the 0.022 means we're going to have an additional amount of people here. So we have a general form of a growth equation. And what that looks like is A equals, we read this as A naught, 1 plus R to the power of N. So A is the final value, okay, or final amount. A naught is your starting value or your current value or your starting amount or your initial amount. N is your measure of time. And R is your growth rate. So in the question, your growth rate will be given to you as a percent, and you would need to change that to a decimal to be able to actually add it to the one. So again, that one is 100% of what you started with, plus your additional growth R. The other type of equation we will see is decay. So the amount that we started with is going to get smaller each time. So this equation here, we've got P equals 100 times 0.87 to the power of t. So you'll see that we've got 0.87 less than 1. That means we're getting smaller. Okay. This is the percentage of caffeine in your blood system over time. So P and T are our variables. So T would be time, how much time has elapsed. And P would be the percentage of caffeine in your blood. So if we want to explain the numbers, we know that that number in front is what we're going to start with. So that would be 100, which would represent 100% of the amount of caffeine we're going to have for that amount of time. So when we start counting the time, whatever amount of caffeine is in our blood, we're going to consider 100%, and then it's going to decay over time. So as time goes on, that percentage will get smaller and smaller. Basically, your body will break down the caffeine. So 100 is your starting percent of caffeine. And the 0.87 represents decay. We're getting smaller as we go over time. Now, our decay rate is not 87%. If we think about starting with 100% or 1 as a decimal, if we then go down to 0.87, we've decreased by 0.13 or 13%. So our decay rate here is actually 13%, because again, if we started with 100%, this is showing we end up with 87%, which means we've decayed by 13%. So when you read a decay question, you need to be very careful with the wording. Sometimes they will say you'll decay to a certain value, and sometimes they will say you decay by a certain value. So if I say you decay to 60%, that means that we decayed by 40%. So just be very careful when you're reading the wording in a decay question. Our general form is very similar to our general form for growth. We still have A as our final value equals A naught, our starting value, times, this time it's 1 minus R to the power of N, where R is our decay rate. Okay, so A is still our final value or amount. A naught is still our starting or initial value or amount. N is still your measure of time. So the only difference here is that R is now your decay rate. So growth, you're going to do 1 plus R. Decay, you're going to do 1 minus R. And again, note that your R will always be given to you as a percent in the question. And you're going to need to change that R to a decimal for your equation. Okay, so have those handy as you're doing your word problems. There are also a lot of other types of word problems that you can encounter. There's some interest or loan questions that have a big, giant, messy formula that's built based on these simple ones, but they're much worse. If you want to see them, they do have some examples in the textbook. But nobody would ever use those to solve that type of loan or investment question. Realistically, there are lots of computer programs that would calculate those things. Um, they're mostly used in this book and in this course to just make a worse question for you guys to try. So I'm going to skip over those, especially because we're doing this online learning bit. So if you would like to see the borrowing or investing questions, you can take a look in your textbook. This is section 7.1, 7.2, and 8.3 in your textbook, which is listed at the bottom of these notes. So again, if you want to take a look at some tougher questions, you can go right ahead and take a look at those borrowing investing questions. So we're going to try a couple questions here. So the first one is the average winning speed of the Daytona 500 since 1910 can be modeled by this equation. So first thing is this going to be growth or decay? So if I take a look, the 132 would be my first year's winning speed, which according to the question is in 1910. Right? N would be the number of years since 1910. And the 1.01 tells me that the speeds are getting faster every year because this shows us that we have growth. My growth rate would be 0.01, which is 1%. Okay, so because this is bigger than 1, we know it's growth. It's bigger than 1 by 0.01, which is 1%. So our growth rate is 1%. Now, we're going to graph this, and for now, we're going to use Desmos because we haven't learned how to graph yet. That's lesson 4. I'm just going to pull up my Desmos here. So we will type in y equals 132 times 1.01 to the power of n. And you'll notice I don't see anything here, and that's because when I have an exponential growth or decay, this 132 is going to vastly dictate where my y-intercept is. And it also depends on the number inside the brackets as well, but this is going to be real high up because it starts at 132. So if I kind of scroll up, I can see that this is what it looks like. So an exponential growth graph will always look like this. Okay, a decay would be something like, let's do that. So it goes down as you read it left to right. An exponential growth goes up as you read it left to right. So we're just going to sketch what this looks like. So what this means is that our first year, we can see here our first year when we start would be times 0, and our speed was 132. As we go along, like if I pick, let's say I pick this one here, this would be year 43, and the speed would be 202.485 kilometers or miles per hour, whatever it is, right? So I can see as I go along, the x coordinate is my n or my time, and the y coordinate is my s or my speed. So years 80, 80 years after, that would be 1990, right? We would have a speed of 292. Okay, so I'm gonna get rid of that. So we graphed it using Desmos. So we're just gonna get a quick little sketch here. So this was S, our speed was our y coordinate, and this was N, our X, time. Okay. And it looked like this. Okay, it went up. This here was a value of 132. So we want to find the winning speed in 1965. So this would be time, right? This would be an N value, but N is not 1965. Remember, N is the number of years since 1910. So since this is 55 years since 1910, our N is 55. So if I want to find the speed, I'd have S equals 132 times 1.01 to the power of 55. Now, this we can just plug right into our calculator. Okay. We don't need, we could use our graph. We could, on our graph, go along our I go back to our little guy here, we could go till we find n is 55 and find it that way. So that's 56, 55.7, but that's going to be, there you go, there's 55. So it says 228.165. So that's what we should get if we plug this into our calculator. Okay, so if I plug this all into my calculator, I get 228.2, and I'm going to assume this is kilometers per hour for now. Okay. So this one, you just plug this into your calculator. Just be very careful. The 55 is an exponent only on the 1.01, not on the 132 as well. Okay. And the next one is, during which year did the winning speed first exceed 250? So this would be an S value. My speed is 250. Okay. So I'm trying to find which year. I want to know N. Okay. So if I plug this in, I got 250 equals 132 times 1.01 to the power of n. And now we're in a situation like we were in lesson 2. We need to try and solve for n. So the first thing I'm going to need to do is divide both sides by 132. Now, as soon as I have a missing exponent, my options are try and make the bases the same, which we can't do here, or log both sides. Now, on the left side, if you want to plug this into your calculator and actually get a number, you can, but be careful. In all these problems, you do not want to round your answer till the end of the question. So if you plug this into your calculator, let me just grab mine, we get 7.8125. If you choose to do that, you need to keep all those decimal places. I'm going to leave it as a fraction. But if you want to, you can figure it out as a decimal, but keep every single decimal place until you're done the question. Okay. So if I log both sides, we know using log laws and the power law, I'm allowed to bring that n down in front of the log. The left side's going to stay the same for now. And then to get n by itself, I would need to divide both sides by log 1.01. So on the left, I'd end up with log of 250 over 132 all over log of 1.01, and that would give me my n. Now I'm going to plug that into my calculator. Again, my calculator, when I type in log, a bracket pops up. So I would type in 250 divided by 132, end my bracket, and then divide this by another log, type in 1.01, end my bracket, and then hit equals. Every calculator is going to be different. You need to make sure you know how to use yours. So try typing this in, and you should get about 64 is your n. Now, it's obviously not in the year 64, but again, remember, n is the number of years since 1910. So we first exceeded 250 kilometers per hour in the year, whatever 1910 plus 64 is, which would be 1970. So if you left this as 64, you're not done. You didn't complete the question, because it's not asking you to find n. It's asking you which year did this happen in. And this happened in 1974, not in the year 64. So if you leave it as 64, that tells me you weren't quite sure what the question actually was asking you to find. Okay? So we've got one more question for today, and it's a bit of a trickier one. So these two that we just did are fairly straightforward. You're plugging in one of your variables and finding the other. Some of the questions will not just ask you that simply, or won't give you enough information to be able to do that right away. Okay, some questions also won't give you the formula. You need to write yourself a growth or decay formula. So that's what we're going to see next. So the half-life, this is important, this word half-life here, of iodine 131 is 8 days. And it's saying how long, so we're looking for n, would it take for a 20 milligram sample, this would be our starting amount, of iodine 131 to decay to 1 milligram. So this would be our final amount. So we know a decay formula. It tells us the word decay here is A equals A naught, 1 minus R to the power of N. Okay. Here we know our starting amount is 20. Our ending amount is 1. We don't know our decay rate and we don't know N. We know that it's going to take 8 days for it to reach half of its amount. But we aren't reaching half. We're reaching 1 milligram. Half would be 10 milligrams. So the problem we have here is we need this before we can find N. This is what we've been asked to find. So in order to find that, we're going to use this half-life is 8 days business. Okay, so if the half-life is 8 days, what this means is when N is 8, our final amount, if we start with 20 milligrams, would be 10 milligrams, right? It would take 8 days for us to get from 20 milligrams down to 10. Okay? And if we know that, we know that we have A equals A naught, 1 minus R to the power of N. A would now be 10. That's what we're going to finish with. A naught would be 20. That's what we would have started with. 1 minus R, we don't know. We need to find this, but our N would be 8 after 8 days. So we can use this half-life is 8 days information to find our decay rate. All right. So if I do that, I'm going to divide both sides by 20 and I get 1 over 2 on the left, and I'd get 1 minus R to the power of 8 on the right. Now notice in our blue equation here, it's 1 minus R that we don't know. So as long as we find 1 minus R here, we're good. We don't actually have to go all the way and isolate for R. We can, but it's just going to be more steps. So in order to do that, I'm going to need to 8 root both sides. So if I 8 root both sides, I get the 8th root of 1 over 2 on the left. And if I 8th root the right, the 8 and the 8th root would cancel and give me 1 minus R. Now, once we have that, we can go back to our 1 equals 20, 1 minus R to the N, and plug this in for 1 minus R. So once I do that, I'm going to have 1 equals 20. We know our 1 minus R is the 8th root of 1 over 2, power of N. So we know this information. If we had isolated for R, what would happen is when we plug it in, the ones would just cancel out and we'll get the same things. It's just a couple extra steps. So in any of the half-life questions or bacteria doubles type questions, I generally will just solve for 1 plus R or 1 minus R, and then you can plug that in and it just saves you just a little bit of time. Now I'm going to rewrite this color as 1 over 2 to the power of 1 over 8. Our radicals, we know our fraction exponents. And then this is all to the power of N. Okay. Now I can divide both sides by 20 and I get 1 over 20 equals, and I'm going to rewrite this exponent as 1 exponent. So I'm going to have 1 over 2 to the power of N over 8. Remember, our exponent rules say that we multiply those exponents together. Now, again, we've got an unknown exponent, so we can either make the bases the same or log both sides. We can't make the bases the same here, so I'm going to log both sides. That lets me bring my exponent down in front of the log. So then I can divide both sides by the log 1/2. Now we've also got an 8 here that's we need to get rid of, so we could multiply both sides by 8. When I do that, I'm going to get 8 times log 1 over 20 divided by log of 1/2, and that will give me N left over. So again, we need to plug all this into our calculator, and we will get 34.58 equals n. Again, n is a number of days, so we would probably round this to 35 days. So any question where you see a half-life question, or it takes 20 days for bacteria to double, things like that, that is not your growth rate or your decay rate, but it will help you find your growth rate or decay rate. So when you set up the question, the problem here is that you do not have R. You know some information that will help you find it, but you don't know it right now. Half is not your decay rate. It's your decay for 8 days. We don't know how long this has been going on for, but we know it's not 8 days, because if it was 8 days, we would have 10 milligrams left. We have 1 milligram left. So we need to use the half-life information here to find our decay rate. And once we do that, we can go back and plug that into the formula we had and find n. Similar, if we were looking at growth and doubling, we would go back and plug that in for the 1 plus r. Okay, so there's a couple of these that I've thrown at you in your board questions if you want to try them. These would be the more difficult question types because it throws people off that you are not given your R. You must find it. Everybody always thinks half-life, oh, my R is 50%, decaying by 50%, but that's not the case. So please try some practice questions. As usual, if you have any questions, please let me know.